Hello everyone, I am Tanu Sharma from BSc Chemistry Honors Final Year. Today my topic of presentation is mass spectrometry from organic chemistry. मास स्पेक्ट्रोमेट्री सबसे पहले इसका इंट्रोडक्शन देखेंगे. मास स्पेक्ट्रोमेट्री इज अ पावरफुल एनालिटिकल टेक्निक यूज टू क्वांटिफाई known materials to identify unknown compounds within a sample and to find the structure and chemical properties of different molecules. It is a microanalytical technique requiring only a few nanomoles of the sample to obtain characteristics information pertaining to the structure and molecular weight of analyte. This technique basically studies the effect of ionizing energy on molecules. Nowadays, mass spectrometry is used in many areas, including pharmaceutical, clinical, geological, and environmental. Introduction. It depends upon chemical reactions in the gas phase, in which sample molecules are consumed during the formation of ionic and neutral species. This will happen by converting the material to charged molecules to measure their mass to charge ratio. Mass spectrometry has both qualitative and quantitative uses. The mass spectrum of each compound is unique and can be used as chemical fingerprint to characterize the sample. History. Mass spectrometry was the first performed at the Cambridge University in 1912 by J. Thomson when he obtained the mass spectra of O2 and 2CO. Mass spectrometry took off in 1930s and advanced technology resulted in the development of double focusing mass spectrometers capable of accurate determination. The modern techniques of mass spectrometry were devised by Arthur Dempster and F.W. Ashton. Mass spectrometer. It is an instrument in which the substance in gaseous or vapor state is bombarded with a beam of electrons to form positively charged ions, cations, which are further sorted according to their mass to charge ratio to record their masses and relative abundances. Mass spectrum. It is a sorted collection of masses of all the charged molecular fragments produced. The relative abundance of each is the characteristics of every compound. The mass spectrum can give detailed information about composition of an organic compound and the position of functional group, and is also used for the determination of molecular weight. Principle. In mass spectrometry, organic molecules are bombarded with a beam of energetic electrons, 70 electron volt, in gaseous state under pressure between 10 raised to the power minus 7 to 10 raised to the power minus 5 mm of Hg using tungsten or rhenium filament. Molecules are broken up into cations and many other fragments. These cations molecules or parent ion are formed due to loss of an electron, usually from n or pi orbitals from a molecule, which can further break up into smaller ions. Fragment ions or daughter ions. All these ions are accelerated by an electric field, sorted out according to their mass to charge ratio by deflection in a variable magnetic field and recorded. The output is known as mass spectrum. Each line upon the mass spectrum indicates the presence of atoms or molecules of a particular mass. The most intense peak in the spectrum is taken as base peak. Its intensity is taken as 100 and other peaks are compared with it. Basic principle of mass spectrometry. Mass spectra is used in two general ways: to prove the identity of two compounds, to establish the structure of a new compound. The mass spectrum of a compound helps to establish the structure of a new compound in several different ways. It can give the exact molecular mass, it can give a molecular formula, or it can reveal the presence of certain structural units in a molecule. A mass spectrometer. It is an instrument which generates a beam of positively charged ions from the sample under investigation. Produce ions from the sample in the ionization source. Separate these ions according to their mass to charge ratio in the mass analyzer. Eventually fragment the selected ions and analyze the fragments in a second analyzer. detect the ions emerging from the last analyzer, and measure their abundance with the detector that converts the ions into electrical signals. Process the signals from the detect that are transmitted to computer and control the instrument using feedback. Components of a mass spectrometer. The essential components of a mass spectrometer consist of a sample inlet, an ionization source, a mass analyzer, an ion detector vacuum system. Inlet system. For solids, for liquids, for gases, mass analyzer, quadrupole, magnetic sectors, time of flight, ticker, ticker. Ionization mechanisms: protonation, deprotonation, cationization, electron ejection, electron capture. Ionization source: ESI, MLDI, FAB, FD, PD, APCI, APPI, EI, CIFI. Detector: electron multiplier, Faraday cup, photomultiplier, conversion diode array. मास स्पेक्ट्रोमीटर का ये डायग्राम है. नेक्स्ट है इनलेट सिस्टम. The system of a sample inlet depends upon the sample and the sample matrix. Most ionization techniques are designed for gas phase molecules, so the inlet must transfer the analyte into the source as a gas phase molecule. If the analyte is sufficiently volatile and thermally stable, a variety of inlets are available. Gases and samples with high vapor pressure are leaked directly into the source region by the help of mercury manometer. Liquids and solids are usually heated to increase the vapor pressure for analysis. Liquid samples are handled by hypodermic needles injections through a silicon rubber dam. If the analyte is thermally liable, it decomposes at high temperatures, or if it does not have a sufficient vapor pressure, the sample must be directly ionized from the condensed phase. Sample introduction method. Direct vapor inlet. The simplest sample introduction method. The gas phase analyte is introduced directly into the source region of the mass spectrometer through a needle valve. Pump out lines are usually included to remove air from the sample. This inlet works well for gases, liquids, or solids with a high vapor pressure. It only works for some samples. Gas chromatography. Most common technique for introducing samples into a mass spectrometer. Complex mixtures are routinely separated by gas chromatography, and mass spectrometry is used to identify the quantitate the individual components. The most significant characteristics of the inlets are the amount of GC carrier gas that enters the mass spectrometer and the amount of analyte that enters the mass spectrometer. Ideally, all the analyte and none of the GC carrier gas would enter the source region. The most common GC-MS interface now uses a capillary GC column. Liquid chromatography. LC inlets are used to introduce thermally labile compounds not easily separated by gas chromatography. These inlets are used for temperature sensitive compounds. The sample is ionized directly from the condensed phase. Direct insertion probe. The direct insertion probe is widely used to introduce low vapor pressure liquids and solids into the mass spectrometer. Next, direct ionization of samples. Some compounds either decompose when heated or have no significant vapor pressure and can be introduced by direct ionization from the condensed phases. These are used for LCMS, glow discharge MS, FAB, and laser ablation. Ionization methods. Ionization methods refer to mechanism of ionization, while the ionization source is the mechanically device that allows ionization to occur. The different ionization methods are as follows. Protonation. Protonation is a method of ionization by which a proton is added to a molecule, producing a net charge of 1 positive for every proton added. Example: more basic residues of the molecules such as amines, peptides, can be achieved through MALDI, ESI, and APCI. Deprotonation. Deprotonation is an ionization method by which the net charge of one negative is achieved through the removal of a proton from a molecule. Example: acidic species including phenols. Cationization. It produced a charged complex by non-covalently adding a positively charged cation adduct. Example carbohydrates. Transfer of a charged molecule to the gas phase. The transfer of compounds already charged in solution is achieved through desorption or ejection of the charged species from the condensed phase into the gaseous phase, commonly achieved through MALDI or ESI. Electron ejection. Ionization is achieved through the ejection of electron to produce a one positive net charge, often forming radical cations. It generates significantly fragmented ions. Example nonpolar compounds with low molecular weights. Electron capture. With the electron capture ionization method, a net charge of one negative is achieved with the absorption or capture of an electron. Example molecules with high electron affinity such as halogenated compounds.